Hello everyone, welcome to this video. In this video, we are going to learn about the Generalized Additive Model using OpenMathAI. So, let's get started. What is a Generalized Additive Model? A Generalized Additive Model is a supervised machine learning algorithm used for regression and classification problems. It is especially useful when the relationship between the input variables and the target output is nonlinear. Unlike linear regression, which assumes a straight-line relationship between the inputs and the output, GAM learns a separate smooth curve for each input feature and combines their effects to make accurate predictions. During training, GAM analyzes how each input variable individually influences the target output. It creates smooth curves that best represent these relationships and continuously adjusts them to minimize the prediction error. During prediction, the model passes each new input through its learned smooth curve and combines the contributions from all input features to produce the final predicted output. We will use a heat exchanger efficiency dataset for the GAM model. This dataset contains 50 data samples. The input features are temperature, pressure, and flow rate, while the target output is heat exchanger efficiency. During training, GAM learns a nonlinear relationship between these operating conditions and the efficiency of the heat exchanger by creating smooth curves for each input variable. Once the model is trained, OpenMathAI uses these learned relationships to predict the heat exchanger efficiency for new operating conditions without retraining the model. So, let's get started. Open OpenMathAI. In this demonstration, we use heat exchanger efficiency by using GAM model. Click Create New Project. Enter the project name as Heat Exchange Prediction. Choose a folder location to save the project, then click Save. To import your dataset, either click Load Example Dataset or browse for Dataset to import your own CSV file. Once the dataset is loaded, verify that it contains all columns before proceeding to model training. Scroll down to view the first 10 rows of sample data. Click Continue to Configuration to proceed. Configure the dataset by specifying the input features and output target. There is also a feature called Ignore, which can be used for columns that should not participate in model training. Select the input and output columns manually or use Smart Suggest for automatic recommendations. There's one more feature, Signal Diagnostics. There's a free columns. First one is column. It's tell which features on the dataset like inputs and outputs name. Second one is VIF if it tells how much correlation of the features. Third column is status if it's OK, moderate, high, redundant, and constant. Review the selected configuration. Click Proceed to Model Design. Choose a model from the available machine learning models. OpenMathAI recommends suitable models and features based on the dataset. For this demonstration, select the GAM model. View the model overview, pros, cons, and real-world applications. Click Proceed to Training. You will see the selected model. Click Train Models. Review the training configuration. Test data split, which determines a percentage of data reserved for testing and validation. Review the model parameters and pre-processing settings. And also another feature is added that is trained from scratch or continue from use model. If you train this model before you use that option, modify the configuration if required. Click Start Training to begin the training process. After training is complete, review the following performance metrics. R-squared measures how well the model explains a variation in the output data. Range 0 to 1. MSE, mean squared error, measures the average squared difference between actual and predicted values. RMSE, root mean squared error, the square root of MSE. RMSE is expressed in the same units as the output variable, making it easier to interpret. Engine time, the time required for the generated model engine to execute and produce predictions. Lower engine time indicates faster model execution, which is important for embedded systems and real-time applications. Fit quality, an overall assessment of how well the model fits the dataset. It is generally derived from tricks such as R-squared, RMSE, and residual errors. Model accuracy is commonly estimated using the R-squared value. Example, R-squared equals 0.95 accuracy almost equal to 95%. Click Fit to Window. You will see 3 types. Fit to Window, comfortable, compact. Then the Clear History. If you click that, it will clear the history before its trained model. Another is deselect and select all trained model for export. Click View Curves. You will see the diagram of R-squared residuals and residuals diagram. Click Math and Code Preview. View the generated mathematical equation and source code. OpenMathAI provides expression of the data, detailed explanation of the expression, and an implementation code. Return to the result page and click Deploy Status. Click Export Model. Choose the required export format. ANSI, FMU 2.0, FMU 3.0, Verilog RTL, VHDL RTL, Python Bundle, ONNX Hub. You can choose any of these formats and export. You can also download the free trial versions of OpenMathAI and Twin Simulate. Thank you. Stay tuned for more OpenMathAI demonstration.